Hello everyone. My name is Deepika Sheel. I am currently pursuing my M.Tech in Environmental Engineering from IIT Kanpur, and today we are here to start a new series which is for the preparation of GATE 2027. So, for that, the very first subject that I have taken is environmental engineering. So, uh, we are going to focus here mainly on two GATE branches. First is civil engineering, and then is environmental sciences. So, basically, in civil engineering, um, there is a subject known environmental engineering, but when we give a separate gate for environmental sciences, so it becomes the different from what we study in environmental engineering subject. In engineering, we talk more about the engineering aspects, but in uh, the environmental sciences, we talk more about the aspects like the chemistry, the physicochemical aspects, about the practicals and things. So we'll be dealing with both the things. Uh, so yeah, and we'll be doing this lecture series in English so that all over the country people can get access to a good lectures. I don't know how it will go on, but it will be decided by you guys. Please support me, and we'll be doing further things, and I want your suggestions also. So if anything you guys need, please comment. So let's start with the very first topic, which is water demand in environmental engineering. So we are studying basically environmental engineering. If you guys will tell me, I'll be doing environmental sciences subjects as well. So first, let's discuss the environmental engineering. So in the water demand, this is the first topic. So we should first of all know why we need a water demand, right? Because see, we guys are doing environmental subject here. So in environment, what uh, we need good quality water for our survival. We need good quality air for our survival, right? Ambience should be of proper uh, there should be proper arrangement in the ambience. We should have proper water, we should have proper air, we should have less noise, less garbage, so that we can have a healthy and happy life. So in terms of that, we need a proper water source. We should have proper, healthy and adequate amount of water with us in a city or in a country. So water demand is what and how much water we need for a city, right? For different purposes that we do in our daily life. So water demand, uh, in water demand, so we'll be using the waters from somewhere. The water can be of from any source. uh, So the water can be from any source. Source can be uh, from the river, right? River sediment source can be from the rain. Source can be the groundwater. Groundwater we also call it as subsurface water, and river water we call it as surface water. Okay, so the sources can be of three types. The types are river water, rainwater, and groundwater. So these are the sources from which water is coming. But can we use the water directly from the source? Like if we would have been in the years thousands of years back, or maybe hundreds of years back, we we might have used the water which is coming into the river because it was pure. We can say it was not that uh, dirty, right? But now we can't take, at this time we can't take the river water directly, so we need to have some kind of treatments to the water, and then only we can use it. Even if the water is from groundwater, we see the groundwater fully clear anyhow. Like if we see the river water, we can see that it's turbid, it's little bit cloudy, muddy, so that thing we will not be using. But if we see the groundwater will be very clear. But are we sure to use that groundwater? Are we sure there is no harmful chemicals, there is no harmful microorganism which might affect us? So that we don't know. So groundwater also needs to be uh, treated. So every type of water, even the rainwater in today's environment, we can't trust on even the rainwater as well, because rain is coming from the atmosphere, and the atmosphere is not at all good these times, because we see the air is polluted. Different types of pollutants are there in the in the air, and when the rain comes from that, this crosses the different the pollutant levels, the rainwater also becomes polluted. So can we use that directly? No. So we can't use any of the water for our safety directly. Obviously people use that, but we should not. Okay. So in water demand, like, so we have source, we have source, right? From the source, the from source, how we take the water, we take water from the help of canals. Okay. And then from the canals, the water comes to the treatment plant, we call it as water treatment plant. And from the treatment plant, the water goes to, now, like if we treat the water and directly, we can't use that, because water, uh, like we need to store for future purposes, or if more amount of water is treated, where will we keep it? We and there is the there is a no more use of human beings for that water, so we need to store that water. So for that purpose, we need to have a storage reservoir, or we call it as service reservoir. And from service reservoirs, we get the water through the distribution system. This is kind of distribution system. So this is how the water treatment and water supply goes from source to the distribution system. And from source to canals, we have pipe 1, we call it as pipe 1, and from service reservoir to distribution system, we call it as the pipes which are carrying the water is pipe 2. So these are the things which come under the from the uh, this is the overall, we can say this is the overall cycle, how the water is going from source to distribution. So this is what we have studied till now. So now let's think, now this is the water source from distribution. Now we focus on the demand thing. Okay. So demand can be of two types, three types. Average demand. So demand can be of three types. So in that we can have the water demand. We will call it as not average demand. We should call it as water demand can be of three types. Annual demand, basically water demand. First is annual demand. So annual demand, if we call it, let's V volume in liters. Second, we get annual average daily demand. Annual average daily demand, which is V per day, right? So there are in a year, if we in a year we are using V volume of water. So for one day it can be of, in a year it's 365 days. So V upon 365, and the unit will become liter per day. And then we have the third demand, which is annual average per capita daily demand. Demand, or we also use the word draft. So both can be water draft, annual demand slash draft, annual average daily draft. Now annual average per capita daily demand. Now per capita, so we need to divide it with the population. So if the city has the population of P, we will be dividing it by P. So the unit will become liter per capita per day. Okay, so this is how the type of demands are there. Now we'll be seeing how much, uh, let's move. So now we'll be seeing how much water is needed for different types of demands. So the types of demand, we can say, we'll be having types of demand. So types of demand can be of, like, the first one is domestic demand. So the domestic demand, uh, and the unit can be, we'll be seeing liters per capita per day in these units. Domestic demand can be of like 135 to 225 liters per capita per day. And then we can see, so the domestic demand is there, then industrial demand. So these are the components which any kind of town or city or a human residential area which is getting developed can have. So can have means industrial. If the city is, it's a big city, there can be industries, right? So industry will be a part of that. And if it is a village area, if there are no industries, so industries, we can exclude this industrial part as well. But domestic will always be there in every case. So domestic demand is 135 to 225 liters per capita per day. And then industrial demand comes. Industrial demand is around 50 to 450 liters per capita per day. If there is industry and that is very heavily dependent on water, it can go up to 450 liters per capita per day. And then we have institutional water demands. So if there is public institution, like schools are there, shopping malls are there, public toilets are there. So, and for the public uh, plantation maintenance, for that also we need water. So there is demand institutional demand, and it also can have 20 to 50 liters per capita per day. And then we come to the fire fire demand. So the fire demand can be of, it can be calculated depending on the population. It depends on the population, and there are so many formulas. And there are so many formulas to calculate it. So let's just discuss the formulas one by one. So first is Queteling formula. So Queteling formula is nothing but, it is 3182 under root P. And all the fire demands come in the unit of liter per minute. So this is Queteling formula, where P, in every formula there will be P, that is population, and it will be in thousands. All right. So this is what the Queteling formula says. Now we have the Freeman formula. So the Freeman formula, okay, the formula is for the demand, right? Demand is in Q. So the Freeman formula is Q is equal to 1136 P by 10 plus 10 liters per minute. So this is Freeman's formula, and let's discuss. Next is National Board of Fire Fire Method. So National Board of Fire Method. So it gives Q as 4637 root P 1 minus 0.01 root P. Everywhere P is the population and it will be put into thousands. Like if you have the city's population is 8,000, let's suppose, then in thousands we need to put, so we need to divide it by 1,000, it will come 8. So here we'll be putting P as 8. So this is how we'll be doing the things. And then we come with the next formula, which is Buston formula. So Buston formula says that you take 5663 root P liters per minute. So these are all the empirical relations. These came after the experiments and their results. So the different people, they have done the experiment. The experiments results were fitted into the formula, and this formula was perfectly or almost perfectly was going on with all the readings. So they have created this formula according to that. So we call it as empirical relations. So this is how fire demand is calculated. Next, we have losses and thefts as well. How the losses come? So the losses come because of uh, the leakage in the pipes, right? So if the pipes is leaking, there will be losses, and thefts is also there. Don't people use the metric water, but they don't connect the meters, and they somehow manipulate the meter, and it comes under the theft of the water. So this is how losses and thefts work, and it is about 10 to 15% of total demand. So this is not a small percentage. It's about 10 to 15% of what total is there. So we should focus on making less losses and thefts in the future, but it's not going on, as we know. So the types of demand includes domestic, industrial, institutional, fire, public use, and losses and thefts. So this is how the demands work. The next point, uh, which is the maximum and average daily demand. Okay, so one thing we need to keep in our mind, that water demand can be constant, but the consumption may vary, right? Like in a day the demand is this much, but it will be consumed uh, differently in different part of the day. Like in morning water demand will increase, in afternoon it will decrease, then in evening it will increase the slight, in night it will increase. So like that, the crest and trough comes into the water demand. Okay, so this is how with the time the fluctuations will be there. Okay, so the fluctuations, if we want to know, so if I say FL as fluctuation, it can be given as maximum demand upon average demand, or we can also give it as average demand upon minimum demand. Okay, so this is what fluctuation is. Like I just told that the fluctuation with time, we can see the demand can be of increasing or decreasing like this. Okay, so this is what, and average will come somewhat like this. So this is what average is there. So this is average, this can be maximum, this can be minimum. So this is how the fluctuations work. So from here we come to the maximum daily demand, and we come to like maximum hourly demand, and we'll be seeing that. So maximum daily demand is 1.8 times annual average daily demand, what we have saw in the like previous page. So annual average daily demand. Okay, and this is what it was, v upon 365. So it will somehow, it will come at as 1.8 into v upon 365. Okay, now maximum hourly demand, I call it as MDD. I call this as AADD. Now maximum hourly demand I will call MHD. Maximum hourly demand is 1.5 times of average hourly demand. 1.5 times of average hourly demand. Okay, so this is how the things work. Average hourly demand. And what is average hourly demand? Average hourly demand is nothing but its maximum daily demand divided by 24. So it's nothing but MDD divided by 24, because it's daily. And then if you want to calculate, uh, if you want to calculate, so we'll be having this maximum daily demand upon 24. Okay, average hourly demand of not any day, average hourly demand of the maximum day, maximum demand day. Okay, so the day on which there was the maximum demand, that day's average hourly demand will be taken. Okay, so this is how maximum hourly demand works. Now maximum so this is how it comes as. So this will also be for the maximum day. So 1.5 and something, we get it as 2.7 into annual average hourly demand. So what is this? MHD. Okay. Now I'll give you like a short shortcut so that you can just remember it. Time and then fluctuation. So this is the fluctuation criteria that we are multiplying. So time, if time is hourly, if time is hourly, we will be having 2.7, the peak factor. Okay, it's peak factor. If the time is daily, then we will be having 1.8. If the time is weekly, the factor will be of 1.48. If the time is monthly, the factor is 1.28, and if it is yearly, the factor will be 1. So this is how you can remember in short, and you will make it easily usable. Okay, so this is how things work in the demand. Okay, now we'll see the next topic, which is for what thing the design should be done. So the maximum hourly design can be done, let's say maximum hourly design. It can be done for with two conditions, or three conditions, but we take two only. So the three condition is QMH. Is what is this MH? Maximum hourly. Maximum hourly. Uh, and then okay, this is first one, and then second is maximum hourly plus demand of uh, fire demand. MH, I should write in short first, FT. So maximum hourly plus fire demand. And then third case is we should have Q maximum daily plus fire demand. Okay, so design can be done on the basis of this and this. We can ignore maximum hourly demand in most of the cases, because maximum daily demand is the only thing that's given. So the design can be of, it should be done for maximum hourly, or maximum hourly, or it should be done for maximum daily plus fire demand, and whatever comes maximum we'll be taking that as the design demand. Okay, so this is how things work here. Now let's have one example. Let's go to the next page. Yeah, so we will see example. Yeah, so let's see one example. So the example is like this. uh, I need to note down the example. So the example is P population is given as 2 into 10 to the power 5 of any area, and annual average daily demand is given 300 liters per capita per day. Okay, then we need to uh, calculate the important type of demand. Find important type of demand, and then we need to calculate the design capacity. We need to calculate the design capacity of all components, like design capacity we need to calculate, right? So yeah, so let's see how to do it. So first of all, we need to find out what is the type of demand. Annual average daily demand is given. So can we calculate the maximum daily demand? So the maximum daily demand will be of 1.8 into AADD. So this is 1.8 into 300. So it comes as okay, and then we need to have per capita. It is in per capita. Then we need to multiply it with the population, 2 into 10 to the power 5, and then it comes as, if we calculate, it comes as, yeah, then it comes as 108 maximum 108 million liters per day. MLD is the unit of million liters per day in short. Okay, so now we'll see, uh, can we calculate maximum hourly demand? Maximum hourly demand is nothing but it's 2.7 into the your maximum daily demand divided by 24, right? So 2.7 into 108 divided by 24, it comes out to be, let's calculate it, 2.7 to 108. Uh, 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 uh. No, this is not how we should go. Remove it from here. So the maximum hourly demand is 1.5 of maximum daily demand. So 1.5 into 108, it comes out to be as 162 million liters per day, right? And so maximum hourly we have calculated, we need fire demand as well. So QFD, what's the fire demand? We have seen four five formulas. So let's use the NBFUH formula. Okay, so from NBFUH formula we have 4637 root P 1 minus 0.01 root P. The population is in 2 into 10 to the power 5, and we'll put 4637 root 2 into 10 to the power 5 is 2, 8, 1, 2, 3, 4, 5, and two zeros are gone. We have 200. 1 minus 0.01 under root 200, that then it will come as 1 minus 0.1 under root 200. So it's 56303, and one more thing, the unit was liter per minute. All right, so it comes as 56303. uh, we can ignore it's 0.08, so we can take this like liters per minute. Okay, but we don't want it, we want it in per day. So per minute, that means in 1 hour there are 60 minutes, and then in one day there is 24 hours. Then we need to calculate it with 10 to the power minus 6 to convert it into million liters. So now the unit will become million liters per day. And if I calculate, if I multiply 60 into 24 into 10 to the power minus 6, I get 81.07 million liters per day. So now I have maximum hourly demand, and I have fire demand, and I have maximum daily demand as well. So the criteria was for design. There were two conditions. Either you take QMH, either you take or you take QMD plus QFD. QMH comes out to be 162 million liters per day, and QMD comes out to be 108 plus 81.07. So it comes 189, 89.0, so 189 million liters per day, and we need to take whichever is maximum. So the maximum one is 189, so this will be our design demand. So CD, so the design demand is 189 million liters per day. So this is the demand. So we have calculated, find the important types of demands. We have find out and find the desired capacity. We have find out the desired capacity. Okay. So this is how things go for the demand questions. Now in next section we'll be seeing the different kind of different kind of things to calculate the population forecasting.